gentlemen, welcome to the next and the last lecture. I hope all of you can hear me and see the slide. But before I start with the lecture, I would like to say something about the laboratory work, the experiment. Next week, we will start with the experiments. I have uploaded a timetable with your names and with the time when you have the lab experiment that will find place in the laboratory SB 316. That is level 3 in the old building in the end of the campus, SB 316, and we will have the most of you in presence, but some of the students take part via Zoom. For the students who take part via Zoom, we use the same link as for the lecture. That means you can connect you like for the lecture, and we will place a camera and a computer directly in front of the experiment so that you can see the students who make the experiment in presence. You can see the equipment what we have there, and during the experiment you can, for example, calculate and the students who are in present put the results into the computer so that you can also cooperate, also if you are not in presence here. Yeah, that is important. The first group will start next Monday, 12:15, the same time as now. And the second group will start 14:30. And then we have the same for the other students the following week. No, I must have a look. The following week, the Monday is a public holiday. I must look. We start Monday the 13th. That is important. In the timetable. Yes, we have now the 30th of May. The next, yes, of course. The next Monday is a public holiday. That means we start with the laboratory work at Monday, the 13th of June. Monday, the 13th of June. Next Monday, the 6th of June, is a public holiday in Germany. But the 13th of June we start. So as I have explained it now. Have you questions for this? The experiment, what we will do is the experiment number 1, calibration. And you have it in the end of your script. You have this experiment, the description of the whole experiment, so that you can a little bit prepare what you have to do then. Other questions? No questions. Okay, then we start with the last lecture. We have had in the last lecture the principles of concentration measurement, the principles of analysis measurement. We have started this, And the last what we have shown was a principle of reflection, what you can do with light, but also with infrared light, ultraviolet light. It's a little bit depending from that what you would like to measure. And now we have a little bit different principle. We have the principle of emission. That means you have a sample and you activate the sample. That can be by radiation, but it can also be by burning. For example, if you have copper and you hold copper in a fire, you see a green light because the resonance frequency of copper is in the green wavelengths. And so every material has one or more resonance frequencies, and you can activate this, for example, also with a high current, so that you get a spark. And this flashlight from the spark, you can analyze what kind of wavelengths are in this spark. That is in many times used for the analysis of the content of metals, different kinds of metals. And you produce a short shortcut so that you get a spark. And this flashlight, what you get, can you analyze which kind of wavelengths are there in, and from this you know what kind of metals are in this mix and how many from the different kinds of metals are in this mix. This is very often used, the principle of emission, also for the check of the input quality of different kinds of metals, but also of different kinds of mix of metals. And when you have an quality check on the input side of your production line, in many cases, it is necessary to check, is that what you get from different metal plates, for example, is this also or fulfill this the quality parameter what you want? That in the copper is so and so much of other metals in, and so on. Yes, I have written it here. The activation can be done by flame, by arc, electrical discharge, ionization radiation, but also with light. We have some, especially biological materials. When you irradiate it with light, you get a different wavelength back. That is the case, for example, when you have oil, many kinds of oil. When you irradiate oil with ultraviolet light, you get light back in the range of blue light, so that you can very easy check, is in this liquid oil or not. You irradiate with ultraviolet light, you see nothings from the ultraviolet light, but when there occur blue light, you know there is oil in this liquid in. Yes, and you can data mine in the same way as we have learned it already, the kind of material what is in, and also the amount of material what there is in. Yeah, the fluorescence, that's what I have spoken already about this with the oil with the blue fluorescence. So, and then have you questions to this? No? Then we get a completely different principle. A completely different principle is a principle of chromatography. That is an extremely powerful analysis method. And the principle is that you have here a separation column. There are some materials in, so that are particles from a special kind of materials. And when you have here a sample input, you have here an carrier medium. Mostly it can be, for example, helium. Normally, when you have not a sample in, you go with your carrier medium through this column. It needs time when it is on the output side. And here you have a detector who is detecting one kind of physical behavior that can be absolutely different. What the detector is detecting, that can the heat transfer, that can also the refraction index, everything what you can detect, that there is a gas or a liquid. You have the same principle also for liquids, that there is a change in the content. And when you give now a sample in, that means and short shot of this gas, what you would like to investigate, a gas mix, for example, or a liquid mix. The column is a little bit different then, but you can use the same principles for gases and for liquids. And this shot of the to investigating gas will carry with the carrier medium through the column. But important is that every kind of gas has a different delay by the column. There are gases who are going very fast through the column, and there are gases who are going very slow through the column, because the attraction to the material of the column is different from gas to gas and from liquid to liquid. That means that you have over this column a separation of the parts of the gas. And in the beginning, you have only the carrier medium, but after a time, you get the fastest gas, and you have to detect that there is on the carrier medium this fast gas, which is going very fast through the column. And important is the time. When do you register this change of the heat transfer, of the optical refraction index, everything what you would like to detect? Important is the time. And when you say, I would like to detect, let me say, CO2, you have at first to calibrate this. You give a short shot of CO2 on your carrier medium, and then you wait until the CO2 is coming through, and you register the time when the CO2 is coming to the detector. When you now have a mix of gases and you have the detection of a component after this time, what you have detected for CO2, then you know that is CO2 in this mix. And so you get over the time the different components. The different components in the gas you have when you would like to know what it is. You have at first to calibrate. When you would like to measure, for example, in a liquid chromatograph, you have gas chromatograph and liquid chromatographs, but the principle is the same. When you would like to measure, for example, you have water in and you would like to measure sugar in the water, solved sugar, then you give at first a sample of sugar in and you measure the time when you have the change on the output side. And when you now have a sample in, let me say from juice, for example, from juice, then you look after the time what you have detected for the sugar, then can you say when you have a peak after this time, then is this peak sugar. You measure also different peaks of other components where you don't know what it is. For example, when you give, let me make an example from the traffic, from the public traffic. When you drive, you should not do that, but when you drive with alcohol, when you are a drunken driver, the police let blow you in a device, but these devices where you blow in, they have a lot of mistakes. And therefore, it is only a sign that you have alcohol in your blood. It's not enough for the court. But when there is a sign, then you have to give a sample of blood, and that will detect it by a liquid chromatograph like this. And the results of a liquid chromatograph are very, very exactly. And that is also enough for the court that you have to pay penalty or lose your driver license and so on. And that means you give blood in, you have a carrier medium that can be another liquid, for example, water. And in the beginning, you have put a shot of alcohol in and have measured when comes the alcohol on the output side. When do you register the alcohol on the output side? And when you put then a shot of blood in and you register after this time for alcohol and peak, then you know that's alcohol. In the blood, you have a lot of other components where we don't know what it is normally. But you can calculate the amount of alcohol in the blood when you calculate the area under the peaks. The area under all peaks represent all components in this blood. And the percentage of the alcohol peak compared to the other peaks, to the area of the other peaks, that is the amount of alcohol in this case. And so you can measure with a high resolution and a high precision special components. But you must know what you would like to measure, and you must calibrate the system to this material. That is for example, in the sports, it's every time a fight between the doping producer and the sportsman who uses, and then the organizations who check it. When there is a substance, when there is a material where we know that is it's a doping material for the sportsman, then you can put it in and can measure when comes this material out. And when you have then a blood or another sample from the sportsman, and after this time comes a peak, you know he has taken this doping liquid or doping material. And the problem is that the underground laboratories, for example, in the United States, you have a lot of underground laboratories. It's a huge crime, but they produce every time new doping material. And when you don't know this is a doping material, then is this material one of the unknown peaks. When you know this material is used for doping, then can you determine the time when it occurs, and then can you also exclude the sportsman and so on, all what is then happens. I will show you 215. I will show you a concrete example. That is a concrete example for a gas or liquid chromatograph. You have here this separation column with the particles in from a special material, and you have here the carrier gas. You go with the carrier gas through this sensor. This is a heated wire, and you see these heated wires on both sides of a bridge, so that the bridge is in balance when you give the carrier gas through the column. And when the carrier gas is coming out on this side, you have the same gas on this heating wire and the same gas on this heating wire, so that the bridge is in balance. But when you now put a measuring gas behind this first sensor in, then the parts of the mix in the gas or in the liquid will be separated. Some parts will be faster going through the column. Some parts of the mix will go slower through the column, and then you get a more or less heating transfer, so that the second wire is cooling down more or less, depending from the mix of the gas what you get here, or the single components of the gas mix what you get here. And what you register is only when the bridge is going in imbalance. What you register is a time when it happens, and the time represents the kind of gas or liquid what you measure here. Yeah, that is a practical example, and we go again back. here. So that is gas and liquid chromatography. And with very good gas chromatographs or liquid chromatograph, you can measure until 100 species simultaneously. You can put a sample in and can detect 100 single different parts of the sample. But when you would like to know what it is, you have, before you measure the mix, you have to look for each medium, when comes it through the separation column. A few questions. Gas and liquid chromatography. Okay, if not, then we have another point, what is for the industry very important, and what is in many cases also very important to assure the quality during transport, during when you carry something, for example, gas. The carrier of gas is the humidity. You have different definitions. You have the absolute humidity, you have the relative humidity. The relative humidity is depending from the temperature, because when you have very warm air, it can contain much more humidity as cold air. And very important is the point when you have an amount of humidity in the air and you have a warm air, for example, with a lot of humidity in, and you cool it down, then the air can not contain so much humidity. And when you cool it down until 100% relative humidity, and you go under this 100% humidity, then you get water. You see it on a window when it is, for example, outside cold, inside it is warm, and the temperature on the window is under this point that the air can contain the humidity, then you get the water directly on the window. Important is also humidity is not fog. That is very important. Fog are small particles, small water particles. But humidity means it is as molecules in the air, not as water particles. Fog are water particles, but humidity are not particles that is completely invisible. Humidity is completely invisible. Fog you can see because that are water particles. So, and now is the question how to measure the amount of water in the air. Of course, you can measure it also with a spectrometer, with infrared light, because water absorbed the wavelengths in the infrared range. But in many cases, the spectrometer to use to measure only the amount of water in the air is mostly too expensive, and therefore in many cases exist other sensors for the measurement of humidity. And I can show you this. Here I have some units. The mass of water in the humid mass of sample, also the dry content in percent. That is an old measure, I must say. The measure of water in dry mass of sample in percent. You see here, this is the same as here, but only in percent now. So that you can, normally we show the percentage of water like this in percent of the relative humidity. When you have the relative humidity, it's depending from the temperature, as I said, and you must know the temperature and can say then at this temperature, it is so much from the absolute maximum what we can have as humidity in the air with this temperature. So, and now some sensors what we can use for the determination of the humidity. And all sensors, or the most sensors, have the problem that they work not an infinite time. They have all a limited working time, because when you give the sensor in a humid air, you have also wasty particles in the air and so on. And what is especially terrible is when you have kinds of oil or fat or something which close the sensor against the humidity. That is a problem. But very cheap is the lithium chloride sensor. This lithium chloride is a salt, an hygroscopic salt, and you see here this, that is the material where an liquid with the salt is in, and then have you here two wires which are not connected. These two wires are not connected. You see, they are separate in this material. And when you have now the airstream around the sensor, the salt take the water from the air, and you get from one wire to the other wire a current. And when you have a high humidity, then you need more current to heat the sample so that it is again dry, that you have a decrease of the current. And you can measure the temperature, what you need to reduce the current. When you have a higher humidity around the sensor, you need more current to heat it up, that it is not anymore so wet. And the point to make it dry, for this point you need an current which is higher when you have more water around, more humidity around, and that can you measure with the temperature. So that you can say the temperature is proportional to the humidity. When it is around completely dry, then you have no current because you have no salty water here. And then you have no current, you have no increase of the temperature, and you measure only the temperature around. And that means the humidity would be 0. But when you have a higher humidity, the salt absorbs the water, you get a current, you heat it up, you have a higher temperature. Higher temperature means here is more humidity around. These sensors are very cheap, but yeah, it is written that the humidity should be higher than 10% because when you have no current here, you need a minimum of current to heat it up, and so it works when it is higher than 10%, but 10% is very low. And the error is lower than plus minus 3%. That is for industrial applications, a very normal value, plus minus 3%. Many sensors are in this range. And therefore, because the sensor is very cheap and very robust, it is often used in the industry. But I have written also here, the disadvantage is you can use the sensor only around about 1 year. It's depending what is additional in the air. But when you have, for example, oil particles in the air, or you have kind of fat in the air, that reduce this working time massive. When you have very, very clean air where only humidity is in, then you come on 1 year or more. Have you questions? Okay, then we have the electrolysis hygrometer. That is, let me say, nearly the same principle. You have here an hygroscopic material in P2O5, and this is here in a tube, which is covered on the tube. And when you have a voltage on, DC voltage connected to the electrodes, the water will separate it in oxygen and hydrogen, and therefore you have again a current, and you can measure this current. This principle is used for very low humidity. When you have a gas where you want to know that there is nearly nothing on humidity in, then you can use this electrolysis hygrometer, but yeah, it's only for traces of humidity in gas. So the next one is very, very often used. When you have a mobile phone, for example, and there is a humidity sensor in, then it works normally according to this principle. The basis is that the relatively permittivity from water is 81. In compare of dry air, when you have dry air, it's round about 1. That means when you have a capacity and you bring in this capacity humid air in, you change the permittivity from 1, when it is completely dry air, to water with 81. And this change the capacity. We have 2 different manufacturer kinds. One is this sensor, where you have aluminum 3 oxide in, and you have a plate on the upper side. It's like a grid. It's like a grid, so that you have every time the holes, and on the other side you have also a plate completely closed on this side, so that you have that you make with acid here holes in, holes which you make with acid in, and so you are free to the air from outside. And when you have a higher humidity, you change from this this part between the plates, you change from air to humid air. And that means from the relative permittivity from 1 to 81. And that change the capacity between the both sides. Important is also that you have not waste on this surface, because the holes should be every time open to change the air. Another principle would be this one. You have a plate under the sensor. On this plate, you have an polyamide film. This is a material what attract water, which attract water from the air. And on the other side of this polyamide film, you have this open wires, so that you have again an capacity between the plate and this on the upper side. And when the air is more humid, the polyamide film contains more water, and then have you the same effect as here, from dry air to water or to an humid air. You have a strong change of the permittivity, and so you can measure a different capacity. How you measure this change of the capacity, that is different. Today, mostly we use the capacity in an oscillation circuit. And when you have an oscillation circuit, you produce a frequency. And when the capacity is changing, the frequency will be changing. That is today the most used way, because you can measure, you can count the frequency. You need not an ADC. When you measure the AC current over the capacity, you can measure also the change of the capacity, because the capacitive resistance is changing. But then you need an ADC, an analog digital converter, to get a digital value. When you use it as part of an oscillation circuit, you have only to count the frequency, and you have immediately a digital signal. That is the advantage. That is valid for both principles. because the principle of the measurement of the humidity is the same. It's a change from the permittivity between the plates from dry air to wet air. A few questions. So, and then we have a third principle. This is, let me say, an extremely precise principle, but it is a lot of things to do to realize it. And therefore, it is only used for calibration purposes, for example, when you would like to calibrate another device, because you have to do a lot. How is the principle? You have two thermometers. You have two thermometers. One is a dry thermometer, and one is a wet thermometer. The humid thermometer. You have water, and you have here a tube around this second thermometer. And then you have an electrical engine, a motor, and you suck the air through both ways to the dry thermometer, where you measure the air of this gas, of the air, for example, and you measure on the other side the gas over the humid thermometer. And when you have a humid thermometer here, it gives a cooling effect, because you know it when you have water on your body, when you were swimming and you come out of the water, the humid is going to the air, and this need energy. So that when you have a wet thermometer and you go with your air over this wet tube on that is like a clothes, like a sock, like socks on the thermometer, and you cool it down. And then is it so, when the gas is really dry, you cool it very down, so that you get a big difference between the temperature of the dry thermometer and the temperature of the wet thermometer. When you have a gas with 100% humidity, the gas cannot take humidity from this close, and the reference temperature is the same with the temperature of the gas. That means 100% humidity in the gas, because you have no difference on both. Important is that the gas speed is high enough. That means around about 2 until 3 meters per second you should have. You suck it with a high speed through, so that you have only the cooling effect, that you have not a saturation on the gas during it is going over the surface of the wet cloth. Therefore, you need a relatively high speed. On the other side, you have a very high precision, low uncertainty, also by higher humidity. When you have a lower humidity, the uncertainty will increase a little bit. But in compared to all other principles, it's a most precise principle. And therefore, this principle is used for calibration purposes. Other sensors you can calibrate with this principle. A few questions. Okay, then the last point, what I would like to say here, I think that's the last point. No, it's not the last point, but a very important point. In many cases, you want not know the humidity, but you want know the point when the humidity is 100% and a little bit higher so that you get water. For example, when you have a gas tube and you transfer the gas from another country to Germany, from Russia to Germany, for example, then it is important that the gas is so dry that you get no water inside of the tubes. But the tubes are going, for example, through the Baltic Sea. They are going on land. So you have different environmental temperatures. And then is every time the question, how much have I to dry the gas that you get no water inside of the tubes, because over the time that would destroy the tubes by rust. And so you have to dry this gas at first. But the drying process needs a lot of energy, and therefore it should be dried only so much as necessary. And to determine this point when the water is going out of the gas, then it will be colder as it would be at 100% humidity. Then when you have 100% humidity in the air or in the gas and you make it colder, then you have the water on the surface. And therefore, to determine exactly this point, you can have a mirror. You can have a mirror. You have a thermometer here, and you have a cooling element. The Peltier element is a cooling element. You can give a current to the Peltier element, and one side is cooling down, the other side is heating up. That means the energy, the temperature will transport from, in this case, from the upper side to the underside. And when you have now here the gas, you have to determine the point when you get water on the surface. You can do that with light. You can do that with light. You have a sender, a photodiode, for example, you have a receiver, and normally you have a clean mirror. But at this moment, when you have water on the surface, you see a lot of scattering light, and you have an increase of the amplitude on the receiver. And with this, you can also control the cooling element, and you can measure the temperature. When is this point? And now you have two possibilities. You can dry the gas. This needs a lot of energy. Or you can heat up the gas, because a warmer gas can contain much more humidity. But of course, the gas to heat up is also in many cases not a good solution. When you have a long tube from Russia to Germany, you cannot really increase the temperature over this long distance, and therefore the normal way is to dry the gas. When you would like to measure this point much more precise, that you recognize this much more earlier as with a light source, you can also use X-ray at this point, X-ray or nuclear ray. When you have a gamma radiation on this point and detector, you can detect this point much more earlier, because water shielded extremely the gamma radiation. And then you detect the point much more earlier as with light. It is also used. So a problem, of course, is that you need every time a clean mirror. And when you have particles in the gas or something, other things, it has the same change of the light scattering as the humidity, as the water at this point, so that you need every time a very clean mirror, and that is in practical applications the most important problem. Therefore, the surface has to clean it and so on. A few questions. So then I have two principles which are very easy. That is that what we use at home. You have in many cases here hair, or meanwhile it is so that you, in the past it was really hair from horses, but today we have artificial materials what we can use, so that you have with the humidity an extension of the hair, and you can show very roughly the humidity, but you have also problems with pollution of the hair. When it is clean, you have an uncertainty from 3% roundabout. For industrial applications, it is okay, but the problem is the pollution. And when you, therefore, this principle is mostly used for home applications. When you buy a humidity measurement device for your home, then can it be that this is in, but today normally not anymore with natural hair. Today we have special materials here. And another material, another principle, what is used in agriculture applications many times, when you have something food for the animals also, and it is on a in a case, then it is important to measure what is the humidity inside of this core materials. And when you have corn, for example, big container with corn, it is important what the temperature is inside, what the humidity is inside. And then you have here a spring where you have an expansion difference between one side of the spring and the layer on the other side of the spring. And one side is normally metal that attract no water. But on the other side, you have a material which attract water and increase the volume. And for this, from this, you have a turning effect by the spring, and you can see here the humidity also roughly, yeah, it's not so exactly as the electronic devices, but it is also usable, especially in the agriculture, because the principle is extremely robust. So, and the last one, what I would like to say is a completely different principle. That is a neutron's humidity sensor. It is used when you would like to measure in a bigger area, the humidity in the ground where you would like to erect buildings, for example, in civil engineering. There is it used when you have a ground, you have here a radiation source, and normally it is a radium beryllium radiation source, and the humidity shielded the radiation very strong. When you have not much humidity in the material, in the ground, then you get more of the radiation which is reflected from something to this point. And important is, this is the radiation source. This is plumbum. I have forgotten to translate it. That is a strong shield, so that there is coming nothing from here to this scintillation crystal. A scintillation crystal is a material which you can irradiate with neutrons, also with nuclear radiation. And the scintillation crystal change the invisible radiation, the invisible nuclear radiation, to visible light flashes, small, very small light flashes. And that can you detect with a photomultiplier. A photomultiplier is an extremely sensitive light detector, so that you get impulses, what you have from the light. But when you have more water in the ground, the water absorbed the radiation, and you get less reflected radiation to the scintillation crystal. This is to measure an average of the humidity in the ground. Round about 1 cubic meter you can measure, and when you measure on different points, you can check a wider area of the humidity. A few questions. This was the humidity measurement, and now I would like to show you very roughly the oxygen measurement. Oxygen plays a very important role in the industry. Let me say, oxygen has one special behavior, or one special what is used for measurement. That is that oxygen is a nearly one gas which is paramagnetic. All other gases are not magnetic. We have some extremely rare gases which are nearly no in the content of the air, which are also a little bit magnetic, but nothing is so paramagnetic like oxygen. And that is a very important point, because nearly all oxygen measurement principles measure oxygen via the magnetic behavior of the gas. You can separate with a permanent magnet, you can separate the oxygen from the air. And therefore, the principles use nearly all this characteristic. Of course, you can also measure oxygen via infrared spectroscopy. That is also possible, but it is much, much more expensive. And therefore, when you would like to measure only oxygen, then you go over you go via the paramagnetic behavior. And I show you some principles. I can make it a little bit short because it is mostly self-explaining. When you have this ring oxygen sensor, we have some companies in Germany, they produce this, Hartmann and Braun, for example. It's one of the bigger producer of oxygen measurement devices. You have a ring here, and you go with your gas inside. When you have, or let me explain at first this one, you have here a bridge, and you have here on the other side of the bridge two resistance as wires, and you run the bridge with a voltage so that these two resistances, these are wires, and they are heated up. The current is so high that you heat it lightly up. This both have a higher temperature. When you have no oxygen inside the gas, both sides have the same stream of gas, and you have no movement of gas in this way. But when you have oxygen inside, then you attract with these magnets the oxygen from the gas from this side, and you get a stream to the right side, because when you heat up the oxygen, he lost partly the behavior to be magnetic. That means you heat up here the oxygen, and you give more oxygen inside, because you attract with the magnet the cold oxygen, and it's you get a movement through this tube to the right side. And the first heater heat up the oxygen, and the oxygen is go to the second heater. That means the first is cooling down and the second is heated up, because the first gives the temperature to the gas is going to the second one, the first is cooling down, the second is heated up, and you get an imbalance in the bridge. And the strongness of the imbalance is a measure for the oxygen. The range is interesting. It covers 0 to 100% oxygen, the full range, and the smallest range can be 0 to 1%. That means very, very small. The uncertainty is plus minus 2%. It's very good. The only ones what is important, that this tube is absolutely horizontal. It must be absolutely horizontal, and therefore you have a kind of water balance on that you can measure, that the tube is not going up and not going down, because when it would be going up, you would increase the stream. You would measure a too high content of oxygen, and when it would going up, you measure a too low content of oxygen. It must be absolutely in a horizontal lay. So the other, I think I can short a little bit, because that is every time the same principle. You have a magnet, you put the gas in, and here you have a hot wire, and you get, we call it magnetic wind, because it's heated up, the oxygen will be less magnetic. It's going up, cooling down, attracted by the magnet, going up, and so you have this wind, and this wind is cooling down the hot wire, and you can measure the content of oxygen. Or a very, very precise instrument, but also mechanical, very sensitive instrument is this one. You have, when you would like to measure the oxygen in a room, in a room, so that you have not a stream through the sensor, that you would like to measure in the air in a room, you have this sensor. You have these two magnets. You have a torsion wire here. This is a mirror. This is a glass ball which is filled with a gas which contains no oxygen. Normally it is helium. Also on this side. And then you have here one ring of a coil. So that when you have gas, when you have oxygen here, it will be concentrated between the magnets and move this ball outside. On the other side, the same. You have a concentration of oxygen because the magnets, and you move this ball outside. But when you have here a light source, you register this movement. This is a photodiode with a gap, and you see in which direction this beam is going, and then you give a current via these torsion wires to this coil, and this current produce a magnetic field and move the ball again inside of this magnet, in the middle of this magnet. And when you have more oxygen, you need a higher current to bring the ball again in the middle of these magnets, because a higher content of oxygen leads to a higher force to move this ball outside. So that in the end, the current, what you need to press the oxygen out of the magnet, this current is the measure for the oxygen. These devices measure also from 0 to 100%. They have an error class of 1%, roundabout. But that is an error class. When you would like to know it more precise, you should measure it exactly, and then it is in many cases much more lower than plus minus 1%. And you can measure in a room, in the air, you don't need and stream. These devices are also produced by Hartmann and Braun, a German manufacturer for measurement devices. Not only oxygen, they produce a lot of different things, not all sensors and measurement devices. So I think that I can cut a little bit. Here we have the same, you have the gas, and here you have a magnet. And so that you attract the oxygen out of this ring, and you get then a different pressure of the right side and of the left side. And here you have a capacity which change the capacity when you get a pressure difference from left to right. But the principle is again to attract the oxygen by a magnet. That's the same. What is maybe interesting is the solid oxygen sensor, because you know it all. That is the oxygen sensor, what you have in your car. Must have what you have in your car to reduce the gases what get out of your exhaust, and to make the burning process very efficient. And for this, you have here the exhaust, that is the exhaust from your car. You have here the sensor in the exhaust of your car, and you have here the outside air. This P2 is the partial pressure from the outside air, and P1 is from the gas from your car, from the exhaust of your car. So, and then have you here a special material and this has the property, when you heat it up to round about more than 350 centigrades, then you get an transport from oxygen from one side to the other side. Where you have a higher concentration of oxygen, you get a transport from one side to the other side. And the aim is that the oxygen content in the gas is the same as outside. When this is the case, you have a perfect burning process. And this so-called lambda sensor, you know it maybe under the word lambda sensor. This lambda you can calculate from the voltage, what you measure between the inner and the outer electrode of this material. The inner and the outer electrode is like a grid. It's like a grid. It contains a lot of platinum, And it's a grid so that the oxygen molecules can going through, but you produce, when you have a stream of oxygen molecules, you produce a voltage from the inner side to the outer side. And you can calculate the voltage, and you can calculate the lambda. And the lambda says when lambda is less than 1, then have you too less oxygen for the burning process. When lambda is bigger than 1, it's too much. And when it is round about 1, then it is the ideal amount of oxygen for a total burning. And when we look for this lambda, you see the voltage is 1 volt, 1000 millivolt. And when lambda is 1, you have an extremely decrease of the voltage. Exactly when lambda is 1. That means for the best burning process, you should be in this in this part of the curve, round about 1. But when we look now for the gases, what we would like to reduce from the exhaust gas, then you see here hydrocarbon, and you see it's below 1, it's going up. And carbon monoxide is going up below 1. That means for this both gases, you should run it over 1. But for the nitrogen oxides, you see it's increasing at 1. But that is also what we not want. And therefore, we run our combustion engines from the cars roundabout at 99.9. That means exactly this point below the nitrogen oxygens start to increase, but over the carbon monoxide starts to increase to the lower values, and the hydrocarbon too. Therefore, our combustion engines from cars should be run in 0.99 lambda. That is this point where you have the lowest content of gases on the exhaust, what we want, what we not want. The gases which are, especially nitrogen oxides, are dangerous for the environment, and we try every time to reduce these gases. A few questions to this lambda sensor. Okay, then we look for another point. Infrared spectroscopy. We have, I can make it short, we have spoken already about the infrared spectroscopy. You have here the radiation source. In many cases, it is light. You have the sample, and then you can you can separate the different wavelengths. You can make it by diffraction or by dispersion. When you have this is by dispersion, but when you have small stripes, you can make it by diffraction. And in the end, you have separated the wavelengths from the minimum to the maximum. and depending from the sample, you miss some of the wavelengths, how much there is missing, that is the amount of content, and the wavelength itself is the kind of material what you have measured. And we have another principle, but it is generally the same. You have here the measuring gas, you have here a reference cell, and you give an infrared light on in a wide spectrum. And here you can fill the receiver with a gas what you would like to measure. And when you have no gas from this kind, what you would like to measure in this measurement cell, then you have an heated up on both sides of the receiving cell in the same way, so that you have no change of the capacity, what you have here. But when you have the measuring gas, here what you would like to measure, here already in the measuring gas, then you have less heating up in the receiving cell, and you measure the difference in the capacity. What kind of gas you would like to measure is depending what you fill in on the receiving cell, so that you can, with this principle, every time measure only one gas, but which gas? You are free to have the choice. This gas, what you would like to measure, you fill in on the receiving side. So I think we must look that we have, yeah, this is the last one. Then it fits also exactly with the, stop here. It fits exactly with the time. We have 2 minutes. And this is also the last point of the lecture. The X-ray fluorescence analysis is a very often used principle, especially when you would like to check the quality of surfaces. How much gold is on the surface of a switch or of another contact also. How when we produce today plugs, for example, plugs and sockets, then you make gold on the surface that you have a better contact. But how much of this gold is on the surface? That is a very important quality question. You want not to have too much gold on the surface, but also not too less on the surface, so that it works perfect and is not too expensive. And how much metal of one kind is on or in the metal of the other kind? This can you measure with X-ray fluorescence. You have an aeration beam and primary beam, and you irradiate the atom of the material, and then you push one electron outside of the atom. And from this, the atom will be unstable. And the atom has the behavior to want to be a stable atom. And therefore, I must look, yes, I have it on this picture. Therefore, this electron, what was pushed out of the atom, will be replaced by another electron from an outer shell. And because the inner shell has a lower intensity as the outer shell, this electron gives a secondary beam. And the frequency and the amplitude of this secondary beam is especially different for every metal what you have in your mix or on your surface, so that you can calculate the energy, and you can also calculate the wavelength, the lambda. And this is the measurement device. You see here you have the radiation source that can be X-ray, that can also be atomic ray. And you irradiate your sample, and you get the secondary beam for each metal with a special amplitude and a special wavelength, so that you get impulses. They look a little bit like mushrooms, but that shall be impulses. And you see, every metal has a different amplitude. And so you can calculate these different amplitudes to the amount of the kind of metals. The wavelengths or the amplitude is typical for every metal, and how many impulses you have. From this, you can calculate the amount of metal. And because to count is very easy, and you can also data mine very, very less concentrations. When you have very less concentrations, you have, for example, here a huge amount of impulses from the basic material, from the copper, for example. But when you would like to measure how many gold is in this copper, then have you very, very less impulses from the gold. Very less impulses from the gold, but many impulses from the copper. But it is then only a question of the time. How long do you measure? And so that you can calculate 20 impulses from gold to 1 billion impulses of copper. And so you can data mine extremely less concentrations. So now I'm 5 minutes over the time. I hope it was interesting for you. And we see us on the Monday, the 13th of June, for the laboratory work. Please download or look in the timetable who is when in the lab, who is when in the lab at which time. And please remember, next Monday is a public holiday in Germany. In May and June, we have a lot of public holidays, maybe because the weather is so nice. Okay, a few questions. Okay, if not, then I say goodbye for today and see you at the laboratory. Bye-bye.
Thank you very much.
Bye, thank you.
Bye.
Bye, thank you.
Bye.